Okay, welcome everyone to step 3 of the water retention curve spreadsheet exercise. If you haven't completed step 1 and 2, please do so before attempting step 3. If you have, then you should have a spreadsheet that looks fairly similar to what you're seeing here right now, with only the question marks in step 3 left to go. You should have the parameters of soil 1 inserted into step 1 and all the question marks cleared. You should have run the solver program already, generated this graph, which compares the pedotransfer function with the Van Genuchten function. This isn't required in the procedure, but it does help to show exactly what the solver function does for you. And yeah, so what we need to do now in step 3 is actually fill in all these question marks here, which is basically just taking these Van Genuchten parameters from step 2, copying and pasting them over here. The other thing that we actually need to ensure we do before we go on and fill in this part of the table is to copy the saturated theta value across as well, which you'll find over there for each soil type. And the reason we need to do these or store them over here as opposed to just targeting these cells is because when we copy and paste the new soil values in for the other soil types, all of these values will change. So we need to make sure we keep them somewhere safe because we're going to need them when we use them in this section of the table over here. Okay, so to begin with, all we need to do is grab those 4 values, say copy, and then paste as values, right? Then we also need to grab the saturated water content or saturated theta value, say copy, and paste it over here. Paste as a value, right? That's actually all the information we need from soil number 1 to be able to generate the values in this column over here. Okay, but I'll get to this column a little bit later. Let's actually have a look at what we need to do to get the values for soil number 2. If you've done everything or followed me up to this point, then all you should need to do is copy those values and paste them in over there as values, right? The percentage sand should change, your saturated theta should change, right? You should notice that these graphs have separated again because we now have a different set of values in the pedotransfer function. All of these values that have changed automatically as soon as you put those new values in there, right? The old Van Genuchten function, which is still here, this hasn't changed from soil number 1, you can see no longer lines up with the new pedotransfer function graph. Right, so to make sure that our new Van Genuchten parameters give us a function which lines up with the new blue line down there, we need to just run the solver again. So you can see that number's not as small as it was before. So that means there's a bigger difference between the values here and the values over here. Okay, so target that cell, click solver. All these settings are exactly the same, so you don't need to change anything there. All you need to do is run solve, right? And you can see the graphs have now lined up and we're happy with that solution. These values have changed, so you can just click OK, grab those 4 values, click copy, and click paste as values. Okay, if you paste as formulas, as soon as you hit that solver button again, the values stored here will change as well because the formulas will still be targeting cells everywhere else. Alright, so you have to make sure that when you're pasting here, you paste as values only. Okay, and that's really it. You just can carry on now and do the rest of the soils. Alright, so soil number 3, copy, paste as values. Right, again, the graphs have changed, these values have changed, the theta sat has changed. Oops, but we forgot to grab the theta saturated from before. So let's just put number 2 back in there. Grab this value here, which we need to actually go there. Okay. So the sequence should be get the soil, copy it, paste the values in, grab the saturated theta, copy that, paste it there. Alright, notice the graph separated, click on the solver, run solve. Right, graphs have lined up, click OK, grab the new Van Genuchten parameters, copy them, paste them there. Right, do a quick check to make sure that we've got both the theta sat and all our Van Genuchten parameters. Then grab the next soil, soil number 4, copy, paste, grab the new theta sat, copy, paste as value. Graphs are separated. This is a bigger number, so we need to run the solver again. Solve. Right, graphs have lined up. Click OK. Grab these values, paste as values. Got a theta sat there. Grab soil number 5, copy, paste it in. Grab the theta sat, paste that, then run the solver function again. Lined up nicely. Grab the Vanderbilt parameters, copy, and paste. Right. Now all that's left to do really is fill in this table and then these few other question marks down the bottom here. So in this cell, which is P14, what we need to do is put the Vanderbilt function in there, but now instead of targeting these matrix potentials, which we were targeting before when we entered the Vanderbilt function here, those were the matrix potentials we were targeting. We now need to target this matrix potential here. So the easiest way to actually do it is to just copy the function from here and paste it there as a function, right, which is that one there. The only thing is we're targeting the wrong cells, right? So you can see here we're targeting a cell that's actually got nothing in it. This is actually the matrix potential G14, which was over here before, right? But we want this one to actually be here. So all we need to do is delete that, hit delete, then click that cell over there. Right? That's changed the target now to N14. The other thing we want to do is we want to change the theta r, alpha, n, and m to theta r, alpha, n, and m over here. Right? And the reason for that is because we are actually going to need to copy the formula across to this soil's parameters, and that soil, and that soil, and that soil. So there's no point leaving these targeted over here. It's just not going to work. Right? So we need to change the theta r, which was K20, but is now going to be, let's see, P6. Okay, so we can just change that to P, and then 6. And the same thing for this one over here, P, and 6. Right. Then we need to change the alpha, which is this one here, to P7. P7. You can see we've moved it over there now. We need to change this one to P8. 8. And the final one to P9. Okay, so now we're targeting this matrix potential here and these soil parameters over here. The other thing we need to change is obviously target the theta sat over here instead of the theta sat over there, right? Which is this one here. So this will be P, and it looks like it's 45. So change that to 45. Okay, and then we can hit enter, right? So this value of water content at that matrix potential we didn't actually have before, right? But because we've derived a Vanderbilt function, we can now put any value of matrix potential in there that we want. And because we have these parameters, right, which are now here, because we have those, it allows us to predict what the water content of the soil will be at any matrix potential, because we have this Vanderbilt function. Whereas before, with the pedo transfer, all we could derive were these matrix potentials. We couldn't actually, because those are the matrix potentials that actually had values for A, B, C, D, and E. So anything in between that, we wouldn't have a clue what the water content would be. We could probably interpolate, but how accurate it would be is a different story. Whereas at least the Vanderbilt function will provide you a reasonable level of accuracy of water content for a given matrix potential. Right, so to fill the rest of the column in, it would be fine to just drag the formula down. But to make things a bit easier when it comes to moving the formula across, we need to change some of the things that we fixed. Right, so you can see these values here. As we copy the formula across, we want these cells to shift across as well, which means the letter will change. Right, the numbers will stay the same, but the letters will change. So that means for theta r, for alpha, and for n, and for m, all we need to do is ensure that we don't have a $sign in front of the letter, so we allow the letter to change. Okay, so that means just removing that one there, that one there, that one, that one, this one, and this one. But now the other thing is, as we copy the function across, the matrix potential cell is going to move across as well. We don't want that to happen. That means we actually need to fix the end. But when we drag it down, we need the number to change. So we only need to put a $sign in front of the n for the matrix potential. So click in there and then put a $sign in. Okay, click to the end and hit enter. That should still be working fine for you. If we were to drag this down now, right? There we go. And you'll notice that these values have been filled in for you. What these values are is just the water content here, and that one is the water content there. I'll talk a little bit more about them in a minute. Okay, if we now move this across, we find we've got values there already. Right? In actual fact, you can probably just drag it all the way across, drag it all the way down, and it'll fill it in for you completely. Right? If you want to check that you're still targeting the right cells, just click on any random number in the table and ensure that your matrix potential lines up with the cell that you clicked, as well as your soil parameters and your theta s. Right? If you followed everything I've done so far, it should have worked out quite fine for you. Now we need to actually plot these values, and the easiest way to do that is to just go insert line, gives you a blank graph, move it off to the side, and then go to select data, add the series name. You can just put that cell reference in there, I guess. The series values will be all of these. Right? Click OK. For the x-axis, we use the log of the matrix potential. Right? And you should have got a line that looks like that. Okay? Now, if you want to add the rest of the lines, neat little trick is to just click on the graph so you can see these boxes, right? And grab this box, wait till you've got the arrow like that, and move it across. Oops. And there we go. All your graphs. Right? Pretty simple. I don't like having these lines in here, so I delete them. And that's really what your end result should be. So what you've got here is these are what you call drying curves. So you're starting with a saturated soil, and you're increasing the matrix potential so that water leaves the soil. So you're ending up with less and less water as the water dries. As the soil dries. The reason I'm saying drying curves is because a wetting curve won't actually follow the exact same path coming back up. It'll actually do something slightly different, and that's a different topic which might be discussed in a later lecture. I'm not sure. Okay, now the only other thing left to do is to fill in these plant available water contents, which are down the bottom. And all plant available water content is the difference between field capacity and wilting point. If you don't know what field capacity is or what wilting point is, I suggest you go and look it up, because it's very important, especially if you are talking about anything to do with soils and plants. So the formula for this would just be is equal to that one minus that one. Enter. And then just drag the formula across, and that's it. You filled in everything on the table. So that's step 3 finished. if you have any questions, feel free to post them on Flow, or email them to Margaret and she'll pass them on to me and I can probably answer them for you. Hope you've managed to finish the spreadsheet, and if not learn anything about soils, at least learn a few little tricks in Excel. Thanks for listening.